Okay.
Our speakers are David and Gregory Chunovsky, who give a homage to Bumby.
Thank you very much. And Richard, thank you very much for being present. So, what is a gossip problem? We quote the formulation of the gossip problem from Richard Bamby's paper, which you can see on the screen, published in Siam Journal of Algebraic and Discrete. So the formulation is rather simple. We have n people, n small, each have piece of information. Pairs of them can share whatever information they possess by making a telephone call. So the question is, what is the minimal number of calls which allows to all n people to obtain all the n pieces of information?
All right. So the problem seems to be an early variation called the telephone problem, originating in 1954 about exchange of some fishes of data. So the story goes that the current formulation is attributed to Boyd, but it seems that people remember Paul Erdős also talking about it. However, the real original formulation was not this nice that Bamby presented, but was, pardon me, quite sexist. And we will still, record it. It's important for just historical curiosity. There are n ladies, and each of them knows an item of scandal, which is not known to any of the others. They communicate by telephone, and whenever two ladies make a call, they pass on each other as much scandal as they know at a time. How many calls are needed before all ladies know all the scandal? Well, that's why it's gossip problem, not telephone problem. So the answer is the following one. Most important is the last term. F of n is equal to n minus 4 for n starting at 4. Well, so the story is really complicated in terms of publication because there is a huge gap between original announcements and actual publication. So we basically will try to summarize it. Okay. So the best historical overview, if somebody is really interested in, can be found in the review called A Survey of Gossiping and Broadcasting in Communication Networks. It was actually 1979 report, but it was finally published 9 years later. And there is a publication. The relevant papers from the time when the problem was solved, and it was known as a problem that was solved many times in a period of couple of years, is this one, Baker and Shostak. And then this is a paper of Richard Bamby, A Problem with Telephones. In fact, this paper, not shows in the final format, but ever form was referred to as of 1972. It was published finally in the Siam Journal in 1981. Then there is a Hungarian group, let's call it this way, A Cure for the Telephone Disease. For some reason, people like that paper. And then there is a Harry and Schwenk, and then there is, of course, a Dutch solution. They're basically all called on the telephone problem. So it's a very peculiar problem which arose in the, as they say, good old days. Okay, sorry, guys. Let me get down. All right. So the problem originated in a very simple switching networks of 60s and 70s. But when the networks became more complicated, the telephone gossip problem started changing to adapt to more sophisticated networks where you can have multiple communication at the same time. Okay? Notice the original problem, you basically have this pairwise calls, effectively one after another. So there is a review summarizing the 1990s version of gossip problem, namely Methods and Problem in Communication in Usual Network in 1994. So that's a general formulation. Now, of the 90th gossip problem. You have an arbitrary and directed graph, and you start with one item per vertex from the set of all the vertices. Then at each unit of time, we will call it cycle. Yeah, we'll specify what it means. Each vertex from the set of vertices can perform a mutual, complete, available items exchange with at most one neighbor. Okay, but it all can happen simultaneously for different vertices or pairs of vertices, more accurately. What is the minimal time in terms of number of cycles to complete a full exchange of all items for all vertices? So you first of all have an obvious law about its diameter. If you cannot get from here to there, well, you will not be able to exchange the information. So you will see later we are really interested in grids. So for a grid, S by S grid graph, standard square graph, the diameter is obviously the distance between, let's call it lower left corner to the upper right corner. So that's a lower bound. And in this case, it was indeed proved that the diameter is the upper bound as well, unless it's 3 by 3 grid, when it is one time slot longer. And there are similar results for multidimensional grid graphs. Again, if one of the dimension is 3, it changes the minimal diameter. However, in real life networks now, not 50 or 30 years ago, what we really need to do is to exchange all items, well, gossip. And the reality is that maybe before you could exchange all items in one cycle, when these items were basically tokens or short text. But these days, the items are very large packets. For example, they're videos or files. So that brings the issue of bandwidth and latency of the communication. So gossip problem in realistic computer networks has to change. So to fix the notation from now on, assume that all communications are done in discrete time steps in cycles. A typical cycle these days is 1 nanosecond, 1 billionth of a second. Networks that we consider can be described by undirected graphs, where every edge from the set of all edges is full duplex. So if the edge is from V1 to V2, it means that the data can travel along the V1 to V2, and some other data can travel along V2 to V1 at any given time unit cycle simultaneously. Okay, only one item, which can be a really large block of data fixed size, can travel along each direction of the edge at any given cycle unit of time. Okay, well, one more complication. This is a real network. We need to introduce a notion of pipeline latency in communication. You obviously can send in good network a big chunk of data every cycle, but it doesn't mean that it will arrive to destination immediately in the next cycle. So we will denote by rho the delay in cycles of a transmission of item from one vertex to its neighbor along any of the edges. You can send an item every cycle, but they will arrive to destination only rho cycles later. However, in most of the discussion below, other than the second half, we assume for simplicity that latency is 1. So if you send it in cycle n, the data will arrive to destination in the cycle n plus 1, and immediately can be sent further to the next neighbor at the cycle and will be received in the cycle n plus 2. Well, from practical point of view, the gossip problem, nice term, becomes a term which is more familiar in computer architecture. It's a problem of all-to-all communication, which is anyway what the gossip story was in the first place. Okay. Uh, um, so again, for every graph, we will start with the usual one item per each vertex, and at every cycle's vortex item per every edge connected to the neighbor can send or receive only one item. So now the problem is the total latency of the gossip, namely how many cycles it will take us that all vertices in the graph will have all items in this all-to-all round. Okay. Well, the problem also has a lot of variations. We'll see later. And if you look on this problem for arbitrary graphs, it's complicated. The good news that from practical point of view, we are not interested in arbitrary graphs at all. We're interested only in practical computer networks where the minimization of latency is important, not just a theoretical study. So these are only networks which can be tightly coupled, and moreover, they actually should be buildable in our real world, not in theoretical or virtual world. So if you want to realize some multidimensional graphs as a computer network in a 3D space, that's a very hard problem, which people fight, for many decades now. Everyone, computer architects, which propose crazy Cayley graphs, electrical engineers, which actually have to look at the signal integrity and latency, and mechanical engineers who actually have to assemble the damn thing. This is why we are going to focus only on planar connectivity, or what's called 2.5D packaging, which simply means that we have multiple planar layers which are tightly spaced in the third dimension, really in the tens of microns. So it's kind of like a layered cake, but one can think about it as essentially a planar graph. So if you want to look at something else, well, there is a problem. Assembly of non-planar graph in 3 dimensions, which would take into account the actual volume of realistic cables, is largely unexplored. There is only a single good paper in this whole field. It's a paper of Kolmogorov Bardzin, most likely written by Kolmogorov to help Bardzin to get a job in a particular institution of the old kind. However, people did not really took this paper into account, and there are reasons for that. In addition to volume of cables, there are also unpleasant issues of power distribution and cooling. You can pretend that you can pack a hell of a lot of stuff in 3D space, but how the hell you're going to cool it? That's why we are stuck with the two-dimensional option. So as a result, we are left with planar graphs, and moreover, with the same reason of complexity of connectivity, only with grid graphs. These are connected subgraphs of an infinite square lattice. So, okay, so let's see what we can get for this time of completion of all-to-all problem. Again, we have obvious lower bound diameter. If you cannot get from lower left corner to upper right, well, it won't work. And then we have a second bound, which is a little bit more interesting. Well, guess what? We need to deliver everything to every vertex. So he already has one element, but we have to deliver the rest. So the time is really bounded now by the maximum of this. So to some extent, you can see immediately if you have a degree 1 vertex, in other words, dead end, that's actually going to take very long time. Not the same as the diameter. Okay, it's not all. If you have a latency more than pipeline latency delay, more than one cycle, well, the lower bound becomes worse because you will simply slowly crawl along the shortest path of the longest distance of the two vertices, and you will have to crawl with the latency of problem. Okay. Well, actually, it seems that in many cases, these two bounds are all we really need. So now let's consider first of all full grids. So it's S by S full grid, pipeline latency is 1. In this case, it turns out that the solution of all-to-all Gaussian problem is indeed a combination of those two bounds from below. The diameter, 2 times S minus 1, and S squared minus 1 over 2, a ceiling. Okay? In fact, there is an absolute abundance of such communication patterns. The number of such patterns is on the order of, constant to the power of the size of the grid. You can have many different algorithms. For example, you can simply run greedy Monte Carlo algorithm where you simply try to push stuff until finally you get somewhere, or you backtrack and start again. But there is a very simple algorithm, basically what people in computer architecture do for practical cases. So first of all, and we actually should do it now, it's very important. Consider all vertices in your grid colored in a chessboard style, in 2 colors, well, red and blue, whatever. So neighbors always have different colors. We will use this analog way. Then, as a step 1, run all one-dimensional communication for each horizontal and which vertical line in the grid simultaneously. It's not that much. And then, once you did it, every vertex will distribute the data collected in step 1 vertically. If this data of color 1 along the horizontal line, and the new data collected horizontally of color 2 will be distributed vertically, because you have effectively 2 passes from source to destination going horizontally and then vertically, or vertically and then horizontally. You basically spread everything. So you got this very nice, very good bound, and it seems that should be the end. Well, let's look at the evolution of this solution or its ilk. For the full grid, for 2 examples, S10 and 11. There is a difference between them, which we'll talk a little bit later. We will use a very simple color coding. As individual cells in the grid get fuller with the new items arriving in. So blue is basically very low, and red is when everybody got everything. So this is the case of 10 by 10 grid. So as you can see, the stuff is arising. If you really squint your eyes and move closer to the screen, you actually will see the numbers which tell you which item is arriving on which link. And the lower left corner is just standard numeration of the grid elements. And again, if you just look above, there is an information what time step you are at. And because we need to get all 100 items everywhere, well, I guess we almost finished. So let's go to the next one. This is 11 by 11. So 121 items should arrive at some point. So now watch out. It's really interesting. The grid is getting fuller and fuller in the center and less full at the edges. And the reason is obvious, right? Each guy in the center can communicate with 4 neighbors. Guys at the edges only with 3, and poor guys in the corners can communicate only with 2 neighbors. It will take them a while to get full compared to the guys in the center, which are already full and stop communicating. They don't have to do it. Anyway, you don't have to watch it till the end. Okay, so that's really interesting. The central area of the grid really works very hard, getting full fast, and then it's getting full completely. But the corners are not finished. And the reason is the degree of the vertices. Okay, that's really bad. It doesn't really help us. that central area finishes faster because the operation, which is run by programs that one needs to run into the computer network, will not be finished until every last node is full. From the point of view of power consumption, it's really terrible. Look at it. The central nodes consume power and produce heat at the double the rate of the side nodes. Okay. Moreover, power is being consumed mostly in the first half of the whole duration. And then basically kind of idling, and we can't even use the fact that they're finishing early. Not at all. So what we'll show now is how the power profile looks like in terms of consumption of individual nodes, but still the same algorithm. Okay, so as you can see, guys in the middle already very, very heavily working. And the guys in the sides and corners are kind of, lukewarm. And again, I don't think we need to go through the whole thing. It becomes clear. Wait a little bit, because you will see something very interesting, how finally this guy stopped working with it. Okay. What's the problem, right? Well, the problem is that the use of power during the communication can be represented by the number of edges active in any given moment. Well, guess what? In one-dimensional grid lines, there's absolutely nothing one can do. The central guys on the line will have to work harder, and the guys at the corner don't. They just send their stuff and they do absolutely nothing. Okay? And because our two-dimensional solution was effectively built out of product of one-dimensional parts, we are suffering from this problem. And that would be really a bad story. However, two-dimensional, high-dimensional grids, at least sometimes, don't have to do it in such a stupid way. You can do something a little bit better. So we start with the Hamiltonian cycle. So let's remind ourselves that Hamiltonian cycle is a closed path in the graph that visits every vertex of the graph. Exactly what? Okay, so if you have a Hamiltonian cycle in undirected graph, this will be an induced subgraph. In other words, it has the same vertex, but much fewer edges if your graph is really full. This Hamiltonian cycle is simply isomorphic to one-dimensional torus, not a line, but a torus, a ring of the full size of your vertex. Okay. Well, if a graph in the Gaussian program, has a Hamiltonian cycle, then you solve the problem trivially. You basically send your messages both left and right in both dimensions at the distance of up to half of the diameter. So the all-to-all distribution would be completed in a minimal time that we know we wanted. So here's an example of one particular Hamiltonian cycle in a 10 by 10 graph. So what's important here is that every cell uses just 2 edges instead of 4 and still completes the Gaussian problem in the minimal time. We are not going to have now a problem that, some guys work hard and some, slacking. Okay. So as long as the linear dimension is even, there are many Hamiltonian cycles in the grid. They're always isomorphic, but they really geometrically differ quite considerably. In fact, classification of Hamiltonian cycle in terms of simple transformation is not really completed. There are only a couple of interesting examples. So the number of Hamiltonian cycles is dramatic. Obviously, it's exponent to the power size of the grid. It's one of the things that people like to do is to compute precisely the number of Hamiltonian cycles. And it was completed up to 26 linear dimensions with several hundred decimal digit numbers. But just for a reasonable 12 by 12 grid, the number of Hamiltonian cycles is still huge. But there's a problem. The grid, not square, but any n by m grid can have Hamiltonian cycle only when the product of dimension is even. It's actually easy to see at least in one way. Otherwise, you have to construct simple example. If the product of dimension is odd, then you obviously cannot have Hamiltonian cycle because, as we talked before, you have a chessboard when colors during the pass alternate. So every Hamiltonian cycle, or just a cycle, in a square grid has even length. Okay? Well, it's worse, much worse. For the full grids, it's relatively easy to construct Hamiltonian cycles, many variations of it. For general grid graphs, and grid graph by definition is a subgraph of a full grid. So if this grid graph has poles, in other words, not solid, the term solid is reserved to those which are simply connected. The problem of finding Hamiltonian cycles is NP-complete, and pretty bad problem. However, if this Hamiltonian cycle exists, the evolution of Gaussian problem looks remarkably smooth. Let's try to look. So it's big case, 12 by 12, something which we actually need an application. So, yeah, there is an evolution so far. You can see very interesting thing. All the colors are the same. If you again squint your eyes and look at what is shown in terms of the number of elements in the center of each cell, it's identical. And again, the reason is very simple. It's a ring, and data traveling on a ring, nicely populated uniform. So that's a good story. It's excellent. But again, this guy is 12 by 12. Relatively easy to find it. We don't really have to wait for 124 guys to fill just a couple of seconds. Okay, you get the picture. Okay, this is the case, however, of 9 by 9. And look at it. If you just look casually, the colors are the same, or almost the same. There's slight little variation. If you will look at the text above the picture, you will see that there is variation by 1. And we will explain why. But anyways, the point is that this 9 by 9, guys, is absolutely great. Why? So we showed the video, it looks fine. But the 9 by 9 grid doesn't have an independent. So what did we got? Well, maybe we don't really need a Hamiltonian cycle. Maybe we need something else. So let's make a formulation of the minimal solution of the Gaussian problem the following. So for a graph which has a minimal latency to the solution of all Gaussian problems, find an induced subgraph. In other words, having the same vertices, but much fewer, hopefully, edges, whose Gaussian problem is also solved in the same way, but which have a minimal number of edges. Obviously, if you get Hamiltonian cycles, you get minimal number of edges. The number of edges is equal to number of vertices. Okay. You can change the formulation and ask, instead of having a minimized number of edges ever used, instead minimize number of edges used individually in each time step. From power point of view, it will give us the same benefit. You can even go further, and unfortunately we will have to. Turn the undirected graph, so-called full duplex, into a directed graph. For this, turn every edge into the two opposite directed edges, back and forth. and look at the induced subgraph of this directed graph, which solves the Gaussian problem is at minimal latency, and now minimizes the number of in and out edges for the vertices for each time step. Okay. So again, for even linear size of the grid, the Hamiltonian cycle solves this problem. You can't really do better than that. For the odd, there is no Hamiltonian cycle. So let's see what we can get there. So we go to the cycles in the graph, right? So it's relatively easy to construct a cycle basis of graph. Sometimes people like so-called fundamental basis, which constructed from minimum spanning tree and then connecting hanging, edges, what you call it, from one side to another, making a more complex cycle. Either way, we know the dimensions, number of edges minus number of vertices plus one. Okay, so if you're talking about bases, it means that there is some vector space. And yes, there is a natural vector space of all cycles in a graph. And that vector space actually lives over F2. So it means that when you add two cycles, the common edges are removed. For our purposes, we need to do Boolean operation in cycles. But it means that if the common edge is present, it is being kept. 1 or 1 is equal 1. Okay? In undirected graph, the Boolean sum of two cycles is not necessarily a cycle, rarely it is. It's just a union of cycles. However, this allows us to create this separation for something useful from the point of view of Gaussian problem. We call graph G, always a green graph, a K-Hamiltonian graph, if there are K cycles in G, such that the Boolean sum contains every vertex in G and has a minimal number of edges with this property. So the full grid graph 9 by 9, and for every odd linear dimension, is 2 Hamiltonian, but never, of course, is 1 Hamiltonian. So this basically how the two Hamiltonian cycles look in the 9 by 9 and 11 by 11. Again, if you watch very carefully what you see this, you will notice, oh, there are two vertices which have a degree 3. That's why the number of edges is no longer minimal, the number of vertices. Otherwise, you would have a Hamiltonian cycle, but one more. So it's not S square edges, but S square plus 1 edge. Okay. So there's a lot of those two Hamiltonian cycles, which are non-isomorphic, unlike the case of normal Hamiltonian cycles. Specifically, we are really interested in the odd linear dimension. So for the odd S, this is how many have classes of isomorphism of induced subgraph of the full S by S grid that have exactly S squared plus 1 edges and solve the Gaussian problem in the minimal time. Okay? So, if you think about, what exactly, you would really expect, well, it's basically, we will actually see from a picture that there's a hell of a lot of them. If we will go to the 3 Hamiltonian passes, it will be on the order of S to the power 6. So there's a lot of them. Unfortunately, they all basically produce the same result. They're always non-isomorphic. So we decided to show you the case of 5 by 5 grid and the corresponding 2 Hamiltonian cycle. So basically, you can immediately see the pattern. You effectively cut, shrink a circle, cut it, put the odd number of vertices in the middle, and each of these guys is really good enough. Well, if you will ask which one of them is really best from the point of view of the power, this will be the second from the left and the second row from the top. He actually gives a slightly better performance. They all complete in the same time, but performance is a little bit better for this type of graphs. So let's see what we have here. All right, the question is why we are doing it. This is really important. So think about it. The total power used during the Gaussian problem is basically the same. It's not really true that somehow you actually use less power total. You basically have to deliver your item to every guy. Yeah, if you will use a particularly stupid algorithm and a long path, you will waste more time. Or you can deliver the same item multiple times. We assume that you're not doing it. What we are trying to reduce is the power variation. What we are really fighting is not as much as the total consumed power, but spikes of it. These are called transients of power variation. If you have a transient, it's basically the same effect if you hit, to think about whatever you're doing is similar to, say, membrane. It's like you hit a membrane corresponding to the bound state, right? It will start, rather violently shake. This is what we are afraid. We don't want spikes. We want smooth transition from idle state to the, back to the idle state at the end of the Gaussian. We don't really want this sudden increase. And it's not a matter of the whole system. It's a matter of getting it for every element of the computer system. Because if one of them will start oscillating, it will affect everyone else. In particular, it actually can create a complete failure. If there would be a very large transient and there would be higher drop, the voltage regulator, I'm talking about from an engineering point of view, simply shut down the juice delivery to the system. We actually talked about bad resonance effect also in the context of the electronic communication. This seminar, it was a talk called How to Break Step. It was an analog of the famous, bridge collapsing when the battalion of soldiers walked in step. This would be actually a similar situation. You don't really want your equipment to fail. So if we have, we know that with the Hamiltonian cycle, we're in a good shape. Using two Hamiltonian cycles, we also have a very good low power variation profile for odd by odd grids. So this is 9 by 9. So you already have seen what would happen if they're using conventional solutions. This is a two Hamiltonian solution. It's, it's almost perfect. This is exactly what. Basically, at every step, on average, we are using only two edges. Some of the direction of the edges do change, but not in terms of the total power. Okay, so far so good. It's really is a good story. We are happy. We got a very weird basis of cycles. Gaussian problem looks good. However, again, reality interferes. The reality is that if you have computer system, even in fact, if you just have computer chips, let's say, sitting on a large module, a lot of computer chips can fit on a large module. In some of the better packaging, you can have over 100 large computer chips talking to each other. And let's say your chips are of reasonable size. What means reasonable size? somewhere on the order of 25 by 30 millimeter on the side. You really cannot easily communicate just on one side. If your system is more distributed, and these are the boards talking to each other, situation is getting worse. Why? Well, even in a perfect vacuum condition, simply due to the speed of light, 1 nanosecond is approximately 1 foot. Okay. You also have to pay a price for the registering, serializing, deserializing, and all that. So it is damn unlikely, unless you do something spectacular with photonics, and nobody can do anything yet, that you would be able simply to have a latency of communication between two chips, or in fact, in our case, a cascade of chips, 1, 2, 3, and so on, just in 1 nanosecond. You would not be able to deliver terabytes of data in such as low penalty. So the pipeline latency of communication between the neighbors in practice inevitably is going to be bigger than 1. So this is our role. It doesn't have to be too large. Remember, 1 foot is a huge distance. You never really want to go more than, say, 6 feet, because that means it's your cable already going to, to cost you a lot and so on. So rho is some, not that large of the parameter. We'll show you. But later. Nevertheless, the problem now becomes different. You have this lambda, which depends on rho as well. Okay? And you can also generalize it to subgraphs. So now you have different bounds. First of all, low bound. It's the diameter times the pipeline latency. This you cannot beat no matter. You also have a trivial upper bound. Take the existing algorithm and simply say, each step takes rho cycles. You don't even have to change algorithm. But it's a terrible upper bound, because now, your latency will start increasing with rho. It's a really a bad story. You don't want it. So what you actually get is something much more interesting. For large linear dimension and a fixed pipeline latency, the maximum latency is only on the order of s squared plus divided over 2 with full grids. You're not really paying too much penalty for adding the pipeline delay. The actual expression is this one. So your first term is the diameter. You can't beat it. It's going to be there. But the second term is a correction on our previous one, which says it was s squared minus 1 divided by 2 ceiling off. So if you substitute here rho equal 1, well, that's exactly what you're going to get, minus 1. So there is a quadratic dependency on rho, but still it's a simple quadratic dependency on s squared over 2. You don't have to multiply the rho. This is really important. Unfortunately, it comes now with a problem. We had this wonderful low power solution for the rho equal 1. Guess what? At least we don't have such a full solution with everything minimized, which would give us this total latency and minimal power variation. So we're actually putting it as an open question. If you don't really know, this algorithm is more or less traditional. It will not minimize the total number of edges. So the open question is, can we actually get a solution with the same latency, which would minimize the number of edges, and as a result, will provide low power variation? So at least for us, it's an open problem. We conjecture that it still will become K-Hamiltonian subgraphs, but now K is bigger than 2. The variety of these subgraphs is huge. There is really no simple way of solving this problem with both upper and lower bounds, especially for the general grid subgraphs, because the only way we know how to solve this problem, let's call it not by Monte Carlo guessing and all that, is to run it through so-called multi-commodity integer linear programming. And it's well known that multi-commodity integer linear programming are NP complete. So we really don't have much chance of solving it this way. And again, there's a damn good reason for that. If such programs would really be available, you would very easily determine for more general grid graphs whether they have Hamiltonian cycle or not. And it's impossible. No, it's NP complete. Right. So the question is really important and non-trivial, because rho is very often has to be bigger than 1. So this is the simplest case that one can show. It's a case of 5 by 5, already non-trivial, and the latency is 2. So what you have here is, if you have undirected induced subgraph, so the number of vertices for 5 by 5 is 25. The minimal number of edges is 27. And this guy is a 3 Hamiltonian path. If you will simply go, all the way and say, no, I'm actually willing to look at the directed graph. I will decouple the links, and they are no longer full duplex. They communicate this way. Well, that's how it look like. Guess what? Instead of, if you would take this guy with 54 bidirectional links, this guy has only 51. Obviously, the minimal number is 50 because each vertex has to talk in and out. Okay? But we don't really know solution for large as bigger than cell. So that's an open. Okay, so what are the practical considerations? Because, we're really interested in practical methods. Okay. So the first of all, if you return back to this last expression of the latency as a function of the grid size and total latency of the Gaussian grid size and pipeline delay, this term is very attractive because the dependency on the linear dimension is linear. This term is less attractive, but it doesn't have a multiplicative effect of grid size time, linear grid size times delay. So what is clear is that we get a diameter, which we really like more than anything else, only for guys, did I lost you or not? Hello?
No, everything is here.
Okay, because I'm getting messages that Zoom quit unexpected.
No, everything is fine.
Okay, fine. Can you still see the
yes, we can see
form?
practical application slide. Yes.
Fine. So anyway, we are talking here about the situation the diameter works as a bound only for limited range of linear dimension depending on the pipeline latency. Otherwise, quadratic term dominates. And that's really a bad story. So here we simply show what happens where. If your latency is 1, well, guess what? Diameter is not really helping you, and the quadratic term dominates. If your latency is 2, in fact, for up to 6 by 6, it's really diameter. And so on. Why it is important? Well, we really never want to go above a pipeline latency of 6 because think about, say, the distance in a good cable vacuum that we are displacing. We are talking about 6 feet. Well, you don't really want to have cables longer than 6 feet, which means that for reasonably large grid sizes, we actually find with effectively linear dependency on the linear dimension of the grid. That's really a very good story. Okay, now more complication. More complication is because we were talking about full grid. You obviously want to assemble the system as a full grid because it's very nice, geometric, easy to assemble. We will assemble it with a good computer subsystem, or mostly good, or all good, depending how good they come out. Unfortunately, as the time goes by, there will be new failures. The failures usually come after the assembly, and most importantly, past burn-in stage. Once you start having defects, the latency estimate is a Gaussian problem compared to the full grid change. How it will change entirely depends on the location and distribution of the defective nodes. Well, at this point, the Gaussian problem becomes really difficult to solve in analytic style. But let's call it topologically, it effectively depends whether you're getting narrow bridges formed in the resulting subgraphs once you remove the defects. For example, that's the worst thing you can imagine. If a defective system has a bad location nearest to the corner, diagonal, or actually nearest to the corner, just next to it on the left, right, or on the other side, what you got is a disaster because your latency of a Gaussian double. Your corner vertex now is a dead end. It has a degree only of 1. And instead of latency being s on the order of s squared over 2, it becomes simply s squared. You double the latency of all to all. That's really a bad exceptional case. We don't really know yet how the minimal latency solution or even minimal latency even should look like in general, because you have to look at a lot of functions of the graph called cross-section bandwidth, also known by the term of Chigger number. And it's not entirely clear how it would look like. Power constraints become even more complicated. Which means that we will need exponential time for solution, even for the moderate grid size. But not always. Let's look at just one bad vertex. It's a nice situation. Maybe at least for a few years of working with your system, you will get only one bad computer subsystem. Okay, so if the bad vertex is not close to the corners of the grid, the new bound is very similar to the one that we showed before for the full grid. Here again, rho is the latency of vertex-to-vertex communication. So it's a little bit different, and guess what? It's actually the second time is lower than the full grid. Well, we lost one element. Maybe it's worth something. However, if the bad vertex is close to the corner, resulting bound would be larger, even if you don't form the dead end or narrow bridge. A particularly bad location is diagonal, 2, 2, compared to 1, 1. You have to actually add a latency of 2 to that expression. But again, those are rare cases. The way how you can examine these k-defective grids, those which have k vertices removed, is you actually look at isomorphism classes. So the number of isomorphism classes of one defective grid exists. As you can see, it's significantly smaller than if you simply remove the one vertex and don't take into account more than just the symmetry. Isomorphism is a little bit better means of separating them. For the isomorphism classes of 2 defective grids, you have a number depending whether it's even or odd. Okay, still about the same order of s to the 4 divided by 16. So when we'll consider these k-defective grids, we will consider only grids which end up after the defect removed as connected graphs which have no dead ends. So the location becomes, as we mentioned before, strongly influenced on the total latency. And it's very similar to the percolation problem. So if you look at the generic set of K defects in the square grid as the grid size grows, we conjecture that mathematical expectation of the latency is this one, provided that the S is sufficiently large with respect to K. We can actually prove it in some cases, and mostly it's done by numerical simulation. It's unfortunate. It's very similar to famous Fisher conjecture of the tiling of the grid graphs resulting from the K defects. The best result in this area still are based on finding L Hamiltonian structures in K defective grids for L at least as large as K. Okay, so we will finish this talk with a little relation of percolation problem and tiling of the grid graphs. There is clearly some vague relationship between especially lower power variation Gaussian problem and tiling problem for general grid domains. Tiling problem is really means what it is. You have a grid and you want to put dominoes in it, maximum number of dominoes which will tile. It's especially interesting in the bond percolation problem for square grid graphs. So bond percolation problem arises in full square grid graphs when you have large number of side effects. So formulation of percolation problem is the following. You want to keep sides in the full square grid with a probability P. Think about Bernoulli trial, flipping your bet coin. Sides which are not kept are removed. As long as the probability of keeping is, rather probability of removing is small, your resulting graph is connected. So that's a probability. If you start removing more guys than this one, you will fail to get a connected graph. Once you have a percolated grid graph, the question is how you can cover it with the dominoes in a minimal number of singles, monomers. In the case of generic defects, this is actually related to the coloring of your sides that you're removing. In the case of small number of defects, one can see actually a good relation between classical results of the percolation, known as the Gomery theorem, and whatever we are doing there. Gomery theorem is actually interesting thing. So you know that 8x8 graph, 8x8 chessboard has a Hamiltonian cycle. If you go along Hamiltonian cycle, you create a domino tiling. Okay. Now, the problem, one of the first problem of this type in Gardner quizzes was if you remove two opposite sides from the chessboard, will you be able to tile? And the answer obviously is no, because you remove two cells of the same color, and you no longer can tile it. You cannot do anything about it. Okay. Gomery theorem in this respect was something interesting. He said, what if I remove two cells from the chessboard which are opposite color? Would they be able to tile? And the answer is yes, because what you do, you simply remove 2 points in a Hamiltonian cycle, but each of them continues to be even, and you can simply put your dominoes along the fractured path. So there is some interesting relationship between percolation and tiling and what we are trying to do with the Gaussian problem. But unfortunately, in both cases, it's mostly conjectures, no proofs. I think that's it.
Thank you. Are there any questions for our
Thank you,
speaker?
and thank you, Dick Bumby. Thank you.
Questions, comments? Volunteers to speak next week? Thank you, Gregory.
Thanks, Mel.
Thank you, Mel. Dick, it's very nice to see you.
Wow. Very quiet group. Oh, Leonid, good
Yeah.
to see you.
I also.
Now that I don't have to tell you you owe me papers, you can show up in person.
You mean my paper?
No, I said, now that I no longer have to send you emails asking you to send me the final version of your papers, because I got them. Now you don't have to be afraid to show up in person.
No, I'm not afraid.
Right. All right, everyone. Wherever you are, I don't know, but here in New York, it's a lovely day. In Hawaii, it's probably always a lovely day, but
Yeah.
we do have a couple of empty slots left in this semester. So if anyone would like to give a talk, just please send me an email and we can work something out.
Yeah.
If there are no questions, comments, jokes to tell, we can quit for the afternoon. And I can go back and find out what Hilbert's inequality is useful for in the large sieve.
Oh.
Okay. All right. Be well, all. See you next week.
Goodbye.
See you next
Goodbye.
Bye.